Hello friends, welcome to this video on direct displacement based design. The previous part was given in the immediately preceding video in this channel. In the present video we shall be discussing the background for the numerical application, and the next video we shall take up actual numerical and solve the problem. So in the last video I asked you to read this literature, Dynamic Behavior of Reinforced Concrete Frames Designed with Direct Displacement Based Design by J.D. Pettinger and M.J. and Priestley of Journal of Earthquake Engineering. Hope you could manage this paper and you have read it. In the previous video we have seen that a multi-degree of freedom system, real system, can be converted to a single degree of freedom system having certain properties. The properties of the single degree of freedom system are called equivalent properties. So it has equivalent mass ME, it has equivalent stiffness KE, and the height of the equivalent single degree of freedom system is HE. If theta d is the displacement, is the angular displacement of the system, then the linear displacement suffered at the top will be equal to theta d into HE as given through this equation. The conversion of the multiple degree of freedom system to equivalent single degree of freedom system was also taken up in the last video. So that conversion gives you the design displacement delta D and effective mass ME and effective height HE. All are given in terms of simple two parameters, the mass of the floors MI and the displacements of the floors delta I. There is a term, the effective time period. It comes from normal time period formula, only giving the effective values of effective mass and effective stiffness. The resulting time period is called effective time period, which will be required in our displacement based design. And just substituting the other side, squaring up and substituting, we get the equivalent stiffness K equal to 4 pi square ME by TE square, and the design base shear is given by Ke into delta D, because force equal to stiffness into displacement, from that it is coming. Now you see, finally we are arriving at a base shear which will be utilized for design of the system, and it is a product of the equivalent stiffness and design displacement. In the design displacement we have considered the design drift. In the direct displacement based design we seen in the last video that only drift can be accommodated, only single parameter. So that is accommodated in the delta D. Further, the nonlinearity of the system is accommodated in the KE, effective stiffness. So we have this single degree of freedom system, and it is suffering a linear displacement delta D at the top corresponding to the design drift in angular form theta d. So we have seen in the last slide that delta d equal to theta d into HE. This is the total displacement it is suffering, and this is also called design displacement delta d. Now this design displacement in terms of linear delta d comprises of a elastic displacement and a plastic displacement. In terms of angular drift, you can also say the total displacement angular drift theta d consists of the yield displacement theta YF, and other part which is not shown here, from here to here, is the plastic angular drift. So this is the background understanding that total displacement theta d will be a combination of the theta YF plus theta P, plastic. Theta P is not shown here, but it is here to here. This theta YF, the yield displacement of the frame, F stands for frame, is given by a simple formula given by Priestley, 0.5 epsilon y LB divided by HB. Here epsilon y is the yield strain of the rebar. Yield strain is given by Fy by Es, the yield strength of the steel divided by modulus of elasticity of steel. LB is the length of the beam concerned, and HB is the depth of the beam. Now depth of beam may not be same every time, or even length of beam may not be same every time. In that case you will get a series of values of theta YF I, and you can take an average for the purpose of design. So the yield displacement as shown here is given by theta yf into He. Now theta yf is known to us through this formula, and multiplying by He I get the yield displacement, linear yield displacement at the top of the equivalent single degree of freedom system. And delta D is obviously theta D into He. Now shape profile is a term. Shape profile indicates the first mode profile of the system, and through research people suggested that the RC buildings will follow a pattern in the shape profile. For building with less than or equal to 4-story height, the shape profile is a linear variation, Hi by H. Hi is the height of the ith floor from the base of the building. Capital H is the total height of the building. In between 4-story and 20-story, the next formula is valid. And if it is more than 20-story, another formula is given here. So through this formula, I can find out the shape profile of any building. Phi I is the shape coefficient. Now Petting and Priestley 2005 in the same paper as we have discussed in the first slide gave another expression for shape profile. Less than or equal to 4-story it is linear, Hi by H, and more than 4-story it is 4 by 3 Hi, 1 minus 0.25 Hi by H. H is the total height of the building. So we shall be utilizing this formula because it is easier to implement. Now let us see the critical story. What is the critical story? Their understanding is required for proceeding further. Critical story is that which is either the greatest interstory height, or it may be having a greatest mass in that floor above. So for this second figure, the ground story is the having highest interstory height. So this we shall call as critical story. In the second figure, the ground story, first story, second story is having largest height. So this becomes the critical story. So let us denote the height of the critical story is HSC. Here also it is HSC. And we have our design displacement theta D. At the critical story, the sway of the frame is delta C. We are giving this notation. And the shape coefficients are phi 1, phi 2, phi 3, etc. for different floors. Let us take a bigger figure of this part to understand further. This floor is moved by certain displacement, the other floor is more displacement, and the differential displacement is delta C, what is shown here. So delta C, how do we get this? From this triangle which is having a height of HSC. So theta D into HSC gives you the delta C, the critical story displacement. So this is the formula, delta C equal to theta D into HSC. Identify the critical story and apply this formula to get the critical story displacement. Now displacement profile of the entire building to be obtained. So this is obtained from the shape profile from the previous slide and the delta C value we have got in the previous slides. So delta I for any ith floor, the displacement of the ith floor is given through this formula. The shape coefficient of the ith floor and critical story displacement divided by critical story shape coefficient. Critical story is a ground story, then phi C will be phi 1. If critical story is third story, then phi C will be phi 3, which you have already calculated because all phi I values already calculated. So phi C is the shape coefficient of the critical story. Now you see we have got the value of delta I, and the floor masses Mi is already known to you from the thickness of the floor, from the live load, from the other loads, and then half of the column load lumped at that level, half of the infill wall, other wall loads lumped at the floor level. Those will give you the mass Mi. So from this value of delta I and Mi, I can now calculate all the properties of the single degree of freedom system, delta D, Me and He. This formula we have discussed in the previous video. Now ductility you have to consider and have to find out the equivalent damping. Ductility is certainly equal to maximum displacement by yield displacement For our purpose, the maximum displacement is the design displacement for which we are designing the system. And delta y we have seen in the last slide, delta y equal to He into theta yf. So this ductility value mu is known to us. Now the equivalent damping for the equivalent single degree of freedom system for RC building is given through this formula, 5 plus 120 into 1 minus 1 by mu under root divided by pi whole thing in percentage. This 5% is the material damping of RC system, and this is the hysteretic damping of the system corresponding to the ductility. Ductility mu is also showing a measure of the damage in the system or nonlinearity in the system, because it is accommodating delta y and delta d. Delta d is equal to summation of delta y plus delta p, the plastic deformation. So mu is accommodating the plastic condition of the system, and as such, utilizing mu I can find out the equivalent damping, because the ductile system, when they are failing with plastic condition, nonlinearity, inelasticity, they reduce the response of the system, or they are acting like a damper. So damage is a kind of damper. So one damping comes to the material 5%, another damping comes to the hysteretic property of the nonlinearity of the damage condition. So that gives the equivalent damping. Now the load combination that we use for design are not the load combinations that you find in the codes. In the codal load combinations, you will find some partial safety factor for load, which is absent here, because code is designing at limit state, or LRFD in case of US codes. But here in this direct displacement based design or performance based design, we design for a particular damage state. So for the present case, what was the damage state? It was the damage state corresponding to the displacement delta D. Initially it was elastic, gradually inelasticity set in the system, and we have taken certain arbitrary point, not exactly arbitrary, through dynamics whatever we got delta D. So this delta D corresponds to some damage which has happened out of the drift we have selected, theta D. So it is a damage state design or damage design, so there is no partial safety factor for loads. So combination is simple: dead load plus live load, dead load plus live load, plus or minus earthquake load in say long direction, and dead load plus live load plus or minus earthquake load in the short direction. So these are the simple cases. You have to calculate the loading due to earthquake in both the directions separately and using the combinations. And furthermore, you are not to use the limited strength of the materials. You have to use the expected strength of the materials. Expected strength also we have discussed in some video in our channel. You can look back. The expected strength of concrete is 1.5 FCK, and expected strength of rebar steel is 1.25 FY as per FEMA guidelines. Instead of using this formula, you can also use the formula we have described in the video when we discuss the strength levels of the materials. So there it will come, value will be slightly different, but you can either use this simple formula or you can use those probabilistic formula for expected strength. Now we calculate the base shear of the building for which you design. This which you have BB equal to Ke into delta T you have seen in the previous slide, and this base shear is to be distributed over the floors for design purpose. So the distribution is very simple. When it is less than 10, then it is BB Mi delta I divided by summation of Mi delta I. So this base shear is apportioned between the floors in proportion to the product of mass and displacement of that floor for ith floor Mi and delta I. So proportional to that it is doing. Now there is some higher mode effects in the building, and this cannot be taken into account by this distribution because we have started with the first mode shape profile. To take into account this higher mode effect, that is modes beyond first mode and other modes, we take recourse to this equation which has been suggested by researchers. If the number of story in the system is more than 10 story, then first you distribute by this formula only 90% of the base shear. So 90% of base shear is distributed from first floor to the roof level, 90%, and 10% we keep in our hand. Now this 10% we put at the roof level. So roof level final force is distribution force from out of this formula in this previous step, Fi roof, and that 10% of the base shear. Researchers have established that with this manipulation of the base shear, you can accommodate the effect of the higher modes in the system. Now let us write down the procedure or the procedural steps for this purpose, direct displacement based design for RC buildings as per Pettinger and Priestley 2005. The data that is given to you is the design drift. As I've said, this DDBD method can accommodate only one target design objective, that is drift. So theta d can be 1%, 2%, 2.5%, 3%, etc. That you'll choose depending on the functionality of the building. For hospital building it can be 1%. For residential building it can be 3%, 3.5%, etc. And apart from that, you have to consider the hazard level in terms of design spectrum of the code. So you can use your Euro code, you can use SCI code or any other code, and you select your level 0.36G or 0.45G or something like that. That will designate your hazard level. So your starter is the design drift and the hazard level. And this step 1 is like this. 1.1, prepare displacement spectra corresponding to design acceleration spectrum at various damping. You can see video number EQ16 in this channel, in this YouTube channel. The conversion is not very hard. You can do it in Excel sheet. Only you have to use that formula. Compute floor masses MI. This floor mass computation, you will consider the self weight of the slab, the finishing of the slab, then half of the column from the top floor and half of the column height from the bottom floor are contributing to the mass in that floor. Then similarly for the wall also, half from the top, half from the bottom. So those will constitute the masses MI at any ith floor. Identify the critical story which is having highest interstory height. If all the interstory heights are same, then you can take ground story as the HSC, the critical story height. Then step 2, 2.1, define the shape profile phi I. So that formula we have discussed. That formula you can use, whatever formula you like. Compute critical story displacement delta C equal to theta d into HSC. So this is required for calculating delta I profile. Compute displacement profile for various floors, delta I equal to phi I multiplied by delta C by phi C. Phi C is the critical story shape coefficient. Compute the equivalent single degree of freedom system properties delta D, ME, HE as discussed earlier. Then calculate ductility and equivalent damping. Ductility is delta D by delta Y, and equivalent damping is by this formula we have discussed, where delta Y, which is used here, is equal to theta YF into HE, and theta YF is the frame yield rotation equal to 0.5 epsilon Y LB by HB. This we have discussed in the previous slide. Now you have to get the equivalent time period from the displacement spectra corresponding to the design displacement and equivalent damping. Find effective time period. So you have converted your acceleration spectrum of the core to displacement spectrum at various damping. Various dampings are required because your damping is this much, and this should be available, or other near values should be available in your displacement spectra. And from there we shall calculate the equivalent time period. Let us see how it works. Yes, so here is the displacement spectra corresponding to some code which I have not mentioned here. So a series of curves you have to draw, displacement spectrum you have to draw a series depending on the different damping. 5% to 30% is drawn here. And how to draw all this we have discussed in the other videos in this channel. And you have your delta D, which you have already computed. So corresponding to delta D, we want to find what is the time period. So you draw a line from delta D horizontally and go up to that spectrum which corresponds to your damping. Say our damping is 10%, then this is the curve. So we have come up to this curve. from delta D. This vertical axis is spectral displacement, so this is giving you the displacement, and delta D is also a spectral displacement because it is displacement of the single degree of freedom system. Now you go vertically downward and come here, so it is 3.5 second. This axis is the time period axis, so 3.5 second is the effective time period of your equivalent single degree of freedom system. So this is the way we get the equivalent time period. Next step is the computation of the base shear. So base shear is BB equal to K into delta D. How to get K? K you get from the equivalent time period T. So K equal to 4 pi square ME by TE square, and then BB is this. Now you have to distribute the base shear for the purpose of design. The distribution formula we have discussed. Then design the building with expected strength. This we have discussed. Why expected strength? Let us just tell one line. Because you are making a damage-based design. So at the earthquake damage states, the building will offer its mean strength. It will not offer limit strength or characteristic strength or extreme strength or anything. It will give an average, where average is mean or expected strength. So expected strength is used in the design as well as in the nonlinear analysis. Evaluate the building and see if drift is satisfied. You have designed for a drift theta d, if the drift is satisfied. For that purpose, you have to carry out the nonlinear time history analysis and pushover analysis also to know the performance level, whatever is there, what is the performance point. This NLTHA will enable you to find out the all the floor displacement from which you can find out the drift, and maximum drift you can take, and maximum drift should not be more than your design drift. Then your design is alright, otherwise you have to redesign. Note that in this process we have not talked anything about the size of the members. So sizes you have taken from your experience: beam size, column size. You have also perhaps applied the capacity design, that is, the column should be stronger and beam should be weaker relatively. Those you applied, and in that process, Priestley and Pettinga, then in their paper, what they've done, they have considered the percentage steel in the beam as varying from say 2% in each face, and the percentage steel in column ranging from 3% to 4%. This variation of the percentage steel will enable you to decide the size of the column and size of the beams. So certainly this will require some iteration, because after design you may see it is not matching with your desired percentage steel, then you have to adjust it, then redesign it, reevaluate it, again carry out the nonlinear time history analysis and see if it is satisfied. So for the purpose of tabulating the values, you have to use this table. Floor numbers: 1 is the bottom story, that is first floor, then second floor, third floor, and up to roof. Then put this next column for height of floors, and then masses of the floors, then shape coefficient phi I using that formula, displacement profile from the formula delta I equal to phi I into delta C by phi C. Then take the product of these two, this column and this column, you get Mi delta I. Then you take square of this Mi delta I multiplied by another delta I, Mi delta I square, and Mi into delta I into Hi product. So for all the floors you can do it. You can write the formula in the Excel sheet and do it very easily and find out the summation of these three columns. These three column summation is required to find out the equivalent single degree of freedom system properties. So up to here in this video, thank you very much for coming with me up to here. The next video will take up the numerical. I shall try to float it today or tomorrow so that the continuity is not lost. Please subscribe the video, like and share it, and put your comments and queries in the comment box. I shall try to answer. Thank you.